Or you have the video?
I'm trying to share the screen. Just a moment. Do you see
Okay,
it?
okay. Yes, I can see that.
Okay, very good. So, hi everybody. My name is Yotam, and I'll be presenting our work on developing a monad for shared state. And this is joint work with Toad Kamar and Nori Lav. So I hope you see the slide numbers on the bottom right, in case you need to reference them. Okay. So in this talk, we will discuss a particular way to find contextually equivalent programs using algebraic effects. And we will follow this general roadmap you see here. So first we define an equational theory, operations and equational axioms over them. So for example, this UU last axiom from the theory of global state. If you update the value in location X, and then you update it again, you can just get rid of the first update because you override it with the second one. So in general, every equational theory induces a monad, which encapsulates the theory. It's useful to find a representation of this monad that's intuitive. So for example, for the theory of global state, the elements of the monad take an initial state and give back a return value and the final state. Once you have this, you define denotations. This step is mostly obvious given that we already have defined our equational theory and operations. We had these denotations already somewhere in our mind. So you can see here, for example, this denotation of this program in two ways. One as interpretation of the operations, the lookup operation, update operation, and in another more explicit way as a function that takes an initial state and returns a pair. Finally, if everything was done correctly, denotations should agree with the operational semantics. So if two programs have the same denotation, then they have the same operational behavior within any context. And this quantification over all contexts is what makes the adequacy theorem useful and powerful. So in this talk, we will look into how this could play out in the concurrent setting. So we'll first review what happens in global state and then dive into the difficulties that arise when considering shared state. Okay, so let's review global state. You can see in this slide denotations of two programs with effects. And there's this chain of global state equations that show these denotations are equal. So for example, one of these equations is the UU last equation that we saw before that allows us to eliminate this update. And thanks to a known adequacy theorem for global state, if anyone knows what I should cite here, let me know later. But we have adequacy for global state. Denotations are equal, then they have the same operational semantics in any context. Just to give an example, consider this context of running the program and then looking up X. And you can see from this particular state, for example, they have the same operational semantics. They end up in the same state and return 1. Right, you're overriding X with Y and then overriding it with Z, so it gets back to 1. Okay, so where did the equations that we used come from? They come from the global state theory, which is due to Plotkin power. So here we have the axioms. The first three have to do with single state interactions. We already saw UU last. There's also UL determine, which says if I update X to U and then I look up X and continue accordingly, then I already know what I'm going to continue with. I know what the value I'm looking up will be because I just updated it. So this equation states that. And there's also LU no op, which says that if I look up X and then update X to the value I just found and continue independently of what I looked up, then I can just continue without these lookup and update. There are also the other equations have to do with interactions with that there is essentially no interaction between different locations. If I look up X and then update Y, I could just update Y and then look up X if X and Y are different. And we list a few notable consequences here, which help us find normal forms for these algebraic terms in the theory. So for example, these two final equations here help us make sure that there is exactly one lookup for each location. Because if I have two, I can eliminate one. And if I don't have any, I can add one. And just as an aside, this equation used to be, originally was one of the axioms, but it was later proven to be a consequence of them. Okay, so moving on to the definition of the monad, right? We defined the equational theory. Now we're defining the monad. And the monad is going to be inspired by the normal form. So as an example, let's take this term, looking up z, and then updating x to what we found, and returning the unit. Using the equations, we can show that this is equal to this term. We look up each location exactly once in order, and then update each location once in order, and then return something. So the idea is that the lookups fetch the state, and then the updates determine what the final state will be. Okay, and this is how we come up with this intuitive set as the carrier. And the interpretations are also rather intuitive. For example, updating. What does update mean? It means that we take the initial state, update it according to what's written here, and then plugging it into the continuation. To the continuation t here. Okay, and what we get is this representation theorem for global state. So in general, a model for an equational theory is a carrier and interpretations that satisfy the equations. And a model on an arbitrary set comes also with a return function, which you can also think of as pure, a monadic pure, which relates the arbitrary set with the carrier. And the model is free. It means that essentially it doesn't have any more information than what the equations demand. There's a precise definition that I won't reiterate here. And once we have this model, we get bind automatically. So we have the carrier, we have return, and thanks to properties that bind has to satisfy in relation to these interpretations, bind is given for free. And note that we'll use this notation for the rest of the talk. Okay, so all of this was global state. Now let's look into shared state and see what changes. So we want an adequacy theorem for shared state. It looks exactly the same, but the programs are different, right? And it's no surprise that something will go bad. So consider this context where we run M in parallel to looking up X. And if we consider the two programs from before, one possible run we could start with this state, with this program, is X being looked up in between these two commands. So X will be 0 when it's being looked up. And there's no way for X to be 0 when it's being looked up in this program. So there's a context in which they behave differently, and so the denotations can't be equal. Otherwise, we won't have adequacy. So we have to let go of something from the original global state setting, either invalidate one of the equations we used or change how denotations are defined. And the second option is what we'll do. We're going to keep the equations, the global state equations, but we're going to add new operations and change the denotations, where the operations will help us take the environment into consideration. So, for example, here, we're going to be explicit about something happening between updating X and looking up Z, just as it was here. But we'll see this, and we'll see this soon. Okay. So just to review, this is the roadmap that we're following. We need to define an equational theory. Then a monad will be induced, but we'll find an intuitive representation for the monad. We'll define denotations. And finally, we hope that adequacy follows, but this is still a work in progress. We've advanced toward this goal, but we still haven't reached it. Okay, so let's start with the operations. So we're keeping lookup and update, but we're adding new operations to reflect the meaning of programs in the concurrent setting. So we're adding an expose operator. Expose X means that another thread did lookup X. Okay, note that expose doesn't bind a value. We have interference, which means another thread did an update of this location to this value. And we also add an operator for choice, non-deterministic choice, because concurrent programs are inherently non-deterministic, the choice of which thread should run. And we're also going to introduce this shorthand of intervening effects. So there's a sum here. We're choosing any choice of any sequence of i's and e's is going to be part of this. And now we can see how we define the denotations. They're just like before, a lookup and an update, but we're putting these intervening effects before and after every local effect. So this is us being explicit about the fact that someone can intervene in between. And we will see if we have time that denotations turn out not to be equal, which is what we wanted, because again, if they were equal, then we'd have a counterexample to adequacy. And because we know there's a context in which they don't run the same. So we're done with the operations. Let's look at the equations. As we said, we are retaining the equations from before, global state. And we also have these single location axioms. IL determine, same reasoning as UL determine. If someone else updated X to U and then I look up X, I know what I'm going to find. No, the point is that someone else updated X to U just before I looked it up. So I really do know what the value will be. There's II last, which is analogous to UU last. Okay, the second right overwrites the first one. And there's EE idempotency, which means that we only care if a value was exposed. It doesn't matter how many times the same value was exposed if it was done in a row consecutively. We also state that different locations commute, though in particular, lookup and expose commute even in the same location, because when I look up or someone else looks up, the state doesn't change. So it doesn't matter in which order this happens. And we also include the standard non-deterministic theory so that the sum operator really does behave like a non-deterministic choice. And we say that non-determinism and other operators commute as well. Again, we have these notable consequences, which help us find the normal form later on. Let's look at the first one. If the environment did this interference, changing X to U, to V, sorry, and then I change X to V, then I can forget about me changing X to V because the environment already did that. And there are subtle points here. Why do I need to remember that the environment is updated X to V? Why not remember that I updated X to V? Okay, but here I don't really need to justify this equation because it's a consequence of the other equations. Right? But again, it's subtle. So let's look at some equations that aren't consequences of the axioms. The first one is the most important, I think, on this slide. So let's focus on that one. We have, if we have an update and then an update before an interference, why not again remove the update? Okay, so it's very similar to what we had before, where we remove the update after someone else updated the same thing. Why not also eliminate the update before? So the problem is that if we have these two together, it implies out of thin air behavior. So to see this precisely, you need to go into the details of how synchronization is defined, and we still haven't shown this. But hopefully you'll believe me that what happens is that if you have two programs that do nothing in parallel, they somehow should be able to update the state if you have these equations and you want adequacy. So obviously we don't want this to happen because we don't have a rule that updates the state from programs that don't do anything. Okay, so this equation is bad. We shouldn't include it. Another option is the equation that's analogous to LU no up, but with I instead of U. And it's the only U versus I global state analog that we haven't included. We thought that it implies that I and U are equal, but that was a miscalculation. So we're still looking into maybe we should include this equation. So if you have any thoughts about this, I'd be very glad to hear. Okay, so considering time, I won't go over the last one, but maybe later if you want to ask about it. Okay, so now that we've gone over the equational theory, next up, the monad. Okay. So let's think about global state. Let's compare it. So in global state, we had functions that take state, right? So this remains the same. But the difference now, one of the two differences is that we're returning a set of pairs. Okay? And this set, the idea is that it's the non-deterministic choices that we can make. Another difference is that the pair is the return value, and instead of states, we have histories. Histories are maps from locations to chronicles instead of values, where the idea is that chronicles don't just keep track of the values, they keep track of all the intervening effects that, at least semantically, all the intervening effects that happened. And not only that, they do so, they only allow certain sequences of these U, I, and E. It's a bit of an arbitrary choice which sequences to include and which not. The point is that you need to make sure that there is uniqueness so that the model will be free. And that we end up with a free model. So there are some rules here about what makes things that make sure that the sequence is unique. I won't go over this exactly, but just to provide one example, this here, the second one on the list, is not a chronicle because one of the rules says that we need a U after every I and every E. And we don't have a U here, right? After this I. There is also an example of a history here. You see a map from locations to chronicles, and even an example of an element of the monad, in particular at the unit set. Okay, indeed, it takes a state, it returns a set, in this case, a singleton set with a pair, where there's the unit, which is in the set, so that's good, and a history. Okay, we're still defining the monad. We need interpretations of the operators. So lookup and update remain the same, essentially the same, though there are different kind of objects now, but it looks like the same formula. And E and I add their respective interference to the chronicle. Okay, for example, expose X exposes at X. This is this map X here, and adds E to the chronicle at X. Okay, so this is an operator that I'm not defining on the slides. Okay, but the notation is suggestive. Okay, so we can't just add an E to the chronicle, otherwise we get a sequence which isn't a chronicle. Okay? Because chronicles always start with a U. So what we do is we add this like no op like U. See, it updates the state to what the state already was at X. So this U, the meaning of this U is don't really do anything. And so this is kind of a technical detail. And the interpretation of the sum operation is just collecting all the choice options in a union. So I've included an example of a calculation. I won't go over it entirely, just note that it looks like the term from before, only we have this E in the middle that I said we'll be explicit about. And once we plug in a state, we end up with a set of pairs. And this chronicle at X indeed does have an expose in it. Okay, so with these interpretations that we saw before and the set we saw before, we have a free shared state model on X. Right, and this is the return function. Again, it's kind of trivial. It takes a state and returns a singleton with, okay, so it's only one pair. It's the thing that we plugged into return, and this is a trivial history. Takes the location and then updates to what the state already said about that location, and no intervening effects. Okay, so now we define the denotational semantics. Most of them are standard. 30-year-old standard here. The only difference is what we do with the programs with effects. And again, the difference is rather small. All we do is we plug in these intervening effects before and after each local effect. You see here and here. We still haven't defined concurrency, the denotations of running two programs in parallel. And we'll do that soon. So this is the example. I don't have time to go into it. So I'll just skip. If you want to, in the Q&A or later, I can go over it. Okay, so now let's define the denotations of synchronization. This is the most crucial piece, right? And the challenge is, when we in general, denotations, the point is that you take a program and you calculate the denotation of the larger program recursively in terms of the denotation of the parts. So we need to somehow define this using the denotation of M and N. So this is the challenge of moving between the semantics back and forth. Okay, we'll see this now using an example. So we want to see what happens where this plays the role of M and this plays the role of N. Right? It's like the example we saw before. This was the program and this was the context here. Okay, what we do is, first of all, we're looking at it state by state. And that's one key thing that took us a while to think about, is when we want to synchronize stuff, we pick a particular state and only sync it at that particular state. And the other thing is always to, right, this is not deterministic. We don't know which intervening effects will happen and which won't. So we only take one option. You see with this E here, and we only take one option from here. Okay, there is no sum operator in either of these. And we sync up deterministic terms. And then collecting all of these synchronizations of deterministic terms, we get all of the options for the concurrency here. So let's go over the synchronizations. You can already see that this kind of matches up. You have L and E, you have U and I, E and L, etc. But you need to make sure that what happens with the state actually matches up. So lookup and expose, together what happens is a lookup. What's Y here? Y here is 0. So when we continue the synchronization, we set this U to 0. And thankfully now it matches the IX0. So this synchronizes to UX0, which updates the state. And now we need to continue the synchronization where X is 0. And so forth and so forth and so on. This thankfully works out. And once we get to the values, we just we ignore the state. It's all okay. And we just return the pair. And now we got a term, an algebraic term, which once we interpret it, we'll get an element of the monad, which will include here at this particular state. Okay, and this is what I wrote here. I wrote the interpretation of what we have here at this particular state is part of the denotation of the parallel execution. So this is the formal definition where this entire thing in notation is this. So I didn't write the formal definition, but again, if you want to ask me about this later, I can show you. Okay, so we don't have the adequacy theorem, but we do have the soundness theorem, assuming M is closed. If it runs a single step, it doesn't add new options. It can only eliminate some of its non-deterministic options from the denotation. And so it's a stepping stone to adequacy. So that's what we have so far. So in conclusion, we've defined an algebraic theory for shared state. We've proven a representation theorem, an explicit definition of the free model as a monad. And we've proven Soundness Theorem. And hopefully we can use this Soundness Theorem and some kind of definition of a logical relation to prove adequacy. We also have other things that we plan for the farther future. And that's it. So thank you very much.
Much for the presentation. There's a few questions, but I think Ohad has answered almost all of them. Or all of them.
Useful odds. Thank you.
Yes, yes, useful to have a quote.
Yeah.
Who is present, right? So you don't. So for others, I mean, please see the discussion in the chat because there is already, I mean, long discussion about this and long comments, and I think that he answered all of those things.
Okay.
Yes. So
Okay.
as Asa said, that weak memory models is the most interesting things. How you can
Yeah.
maybe one my question, not a question, but a comment that adequacy. Yes, of course, it's. I mean, the kind of uneasiness about adequacy that you need to have operational semantics. So now you need to have not only denotation semantics but the operational semantics.
Oh, excuse me, because I didn't actually include it in the slide, but we do have operational semantics.
Yeah.
I mean,
So that's
the
yeah. I
Soundness
kind of
theorem is in terms of the operational semantics. So yeah, we do have operational semantics, but they're just the usual sequential concurrency semantics where everything is. We're using specifically call by value, but that's not the important point. We could also have used call by name or anything similar. I don't think that would affect adequacy in any way. What is very important is that our operational semantics for concurrency are the most trivial ones, one with sequential concurrency, and handling weak memory models will complicate this very much, I think, but that's for the future. Yeah.
But my comment about this, that there is a different version of adequacy, purely denotational, right? You can show the semantics that denotation semantics is adequate if there is two expressions which have equal denotation, then putting in context, arbitrary context that make it a complete program also makes the denotations equal.
I think that's immediate from if you define denotations recursively, I think that's immediate. So
Which
I
is
don't think,
which is actually much easier to deal with this.
again, I don't think it's, I would call it like a simple proposition. If you define the denotations as we have, which
So
is,
at least in some other people, Peter Moses, for example, that's how he defines adequacy of denotation
that's
semantics.
for me that's a weird definition because I'm only familiar with denotations that are defined recursively. I thought that was part of the point of denotations, but if it's a broader
So in
thing
that
that
case, it's adequacy. Well, it means the semantics is gives the correct denotation for the whole program.
Mhm. Okay, so anyway, we mean this the adequacy,
So
not the
you
other one.
mean for the operational semantics. So it's kind of in a Plotkin standard way where you say that operational semantics and denotation semantics correspond.
Okay. Should I try to answer the other questions here?
I think that
Or I can also
okay.
answer
Yeah.
them
So
later. I
there's
don't know.
Andrew Hirsch. So adequacy. Have you thought about preservation of hyperproperties?
I'm sorry. Maybe Ohad can answer because I don't know what that means.
Okay. Well, it's.
Sorry.
I don't know. There's a. I don't know. Ohad answered most of them. So okay.
Okay.
Thank you very much again. And so this concludes the session, and we resume after the break and after the long. After the very long break. So it would be. My time would be 11:30, and Korean time is probably would be 10:30. So in 2 hours. resume in 2 hours. Okay, thank you very much. So see you again in 2 hours. Ohad, can you click on the right button?